Okay, so we've been talking about solving nonlinear inequalities, and specifically last time we left with some inequalities involving absolute value. So let's do one more of those. So solve the absolute value of 3 minus 4z over 5 is less or equal to 8. So, last time we classified three different kinds, 6 different kinds of these. We looked at absolute value of x less or equal to c, and we also looked at absolute value of x greater than or equal to c. So we looked at these, and then for this kind there's 3 possibilities, and for that kind there's 3 possibilities. And so you've got to remember, those 6 possibilities. And so for this one, we could ask, okay, in principle, is it possible that this has any solution whatsoever? So you want to ask, like, is this solution going to be everything? Is it going to be nothing? Or is it going to be just some stuff? So to get an idea, you can just sort of cover that up and just ask, well, in principle, is there anything I could uncover so that in absolute value it would be less or equal to 8? Yeah, right? If I'm covering up an 8, that would work. If I was covering up a 7.9, the inequality would be true. If I was covering up 8.1, it wouldn't be true. Or 8.1 million, that'd be way too big. But also if I was covering up -5, it'd be true. So what's the smallest value I could possibly be covering up? -8. So basically, the argument, the input to the absolute value needs to be between the 8s. And what I mean is that there's 2 8s, the negative 8 and the positive 8. So if we arrange so that the stuff that's in there is between the 8s, then that's the solution. So, last time, if you look at the notes, we called something that was like between the 8s. But it might have been a different number. It might have been like 5, and I would have said between the 5s. So this is the stuff between the 8s. And so, in this case, the first step is to write exactly this. So 3 minus 4z over 5 without absolute value. And what we're saying is that this thing needs to be between the 8s. So -8 less or equal 8. Between the 8s. And now to solve this, we do it in the same way as before. So we'll multiply both sides by 5. Multiply by 5. All positions by 5, really. So that we have -40 less or equal to 3 minus 4z less or equal 40. And then we can subtract 3 from all positions. -43 is less or equal to -4z is less or equal to 37. And now what do we want to do? Divide by -4. So now that is legitimate. The only thing that you're not allowed to divide by is 0. But inequalities are more adventurous than equations. So something curious happens when you divide by -4. What will happen? Yeah, the direction of the inequality will reverse. So now this will be -43 over -4. This will be z. This will be 37 over -4. And the notable difference will be that these inequalities will be pointing the other way. So they're pointing the other way. All right. Other than that, it just proceeds normally. So the negatives cancel, and this is 10.75 greater than or equal to z greater than or equal to -9 1/4. And so then in interval notation, you could write this as -9 1/4 to 10 3/4. And as a plot, like that. Any question about this one? So now, the answer happened to be the stuff between these two numbers. How could we go back in time and edit the statement of the exercise to make it to where instead of this, it was the answer was the stuff between these two numbers, we made it be the stuff that's outside of these two numbers? How could we edit the exercise so that that would be the answer?
You flip the signs, the greater than equal to.
Yeah, we'd flip that. If we went back in time and you know, changed it to where instead of me writing less or equal, if I wrote greater or equal, then it would be the other way around, right? So, you know, an alternate history. Is that if the question was solve absolute value of 3 minus 4z over 5 greater than or equal to 8, now, you know, in principle, is there anything that you can plug in to make the output of the absolute value greater than or equal to 8? Sure, you could plug in 8. And you could plug in 8 million. All that would work. But you could also plug in like -40. That would work too. So you know, this this one, instead of being between the 8s, this would be outside the 8s. And then instead of the first step being this, the first step would be to say that well, we need this thing inside of the absolute value, 3 minus 4z over 5. One possibility is that it's less or equal to -8. That's one possibility. The other possibility is that the thing inside of the absolute value, the input to the absolute value, is greater than or equal to +8. And then this would correspond to the left part. Well, not exactly. More or less, one of these would correspond to the left part and the other one would correspond to the right part. Any question about it? All right. So, now, solving nonlinear inequalities is sort of like a big, a very big topic. And so in order to be able to successfully solve all the nonlinear inequalities that we're going to see in this class, and for those of you that are going to go and take calculus, the kinds of things that you're going to see in calculus, we need a powerful general method. Okay, so in order to motivate why such a method is necessary, in order to show you some places in which it can go wrong, I'm going to give us an exercise. So the exercise is solve 3x minus 2 over x plus 8 is greater than or equal to 1. But I'm going to solve this incorrectly. So if you're going to, if you're going to pay attention and copy all this, please carefully note that what I'm doing is incorrect. So what I'm going to write down is what more or less, in my experience, what a good student would write down if they weren't prepared properly how to solve this. So like if a good student was faced with this for the first time. All right. So then, fine. Want to solve for x. 3x minus 2 over x plus 8 greater than or equal to 1. And, if it was an equation and we wanted to get x by itself, the right thing to do would be to multiply both sides by x plus 8. So I'll do that. The point being is that if you multiply both sides by x plus 8, then that denominator cancels. That's the point. So then you get 3x minus 2 is great, and the x plus 8's cancel, and then this is just x plus 8. And then now I'll add 2 to both sides. (3x) is greater than or equal to x plus 10. And now I'll subtract x from both sides and get 2x is greater than or equal to 10. And then divide by 2. So that x is greater than or equal to 5. All right. So what we're saying, if this is right, the conclusion is that the inequality is true for x greater than or equal to 5, in interval notation 5 to infinity, and written as a plot like this. Okay, so if this is right, then that's what this would mean. So what we're saying is that the inequality should be true for all of these points and false for all of these. So that's what we're saying. So let's double check that. So a point that's right here in this true region is, how about 6? So we're gonna try plugging in 6 and make sure that the inequality really is true. And then a point that's in the false region is, how about 4? So we're gonna plug in 4 and make sure that the inequality really is false. Okay. So let's plug in x is 4. we expect false. So that would be 3 multiplied by 4, subtract 2, divide by 4, plus 8, greater than or equal to 1. All right. So that's 12 minus 2 is 10 in the numerator over 12 in the denominator, greater than or equal to 1. So is that false or true? False. So is that what we expected? Yeah. We expected false. So that's good. That's good. All right. Let's try x equal to 6. So what do we expect? We expect true. Let's check that. So 3 multiplied by 6, subtract 2, over 6 plus 8, greater than or equal to 1. So that's 18 minus 2, so that's 16. 16 over 14, greater than or equal to 1. False or true? That's true. And did we expect true? Yes. So, you know, that worked as expected, and that worked as expected. So far I haven't given much evidence to other than just my word that something nevertheless is very wrong about this. You know, because we did this, and then we said if that's right, then you know this all should be true and this all should be false, and so far it seems to be working out. Okay. Let's try one more point over here. So you know, there's lots of points that are in here. You know, -4, 4 is in there. You know, because it's just stuff to the left of 5. Let's try out -9. So what do we expect?
False.
We expect false. All right. So 3 multiplied by -9, subtract 2, over -9 plus 8, greater than or equal to 1. So that's -27, -29, over -1, greater than or equal to 1. So that's 29 greater than or equal to 1. False or true? That's true. And what do we expect? False. Huh. So something really did go wrong. And you know, you could do this and even be a little bit careful and check some points, and it still might seem right. But something went wrong. Yes?
Like if you divide by negative.
I'm sorry?
Isn't it if you divide by -1 false one?
This?
Yeah.
No, because I didn't do it to both sides. The only time that the direction of the inequality changes is when you do something to both sides. So, like for example, right here we divided by both sides by 2. Does the direction need to change? No, because because 2 is positive. So, you know, we expected false at -9, but actually we got true, so then our answer is not correct. So something that we did is not correct. Well, let's see what happened. We only did 4 things. You can see the stuff that we did in red. So from the bottom up, here we divided by 2. Is that legitimate? Yeah. The only thing you're not allowed to divide by is 0, and 2 is not 0. And when you're dealing with inequalities, if the divisor is positive, then you keep the direction. Otherwise, you reverse the direction. 2 is positive, and we kept the direction. So this is entirely legitimate. This is a subtraction. When is subtraction legitimate? Always. It can never break. So adding and subtracting both sides is always fine. How about this one? Fine. So in some sense, by process of elimination, evidently this is the one that broke it. The very first one. So now the question is how did we break it? Well, so it's an inequality, and we multiplied both sides by something. So remember, the rules are these. So you can multiply both sides by something that's non-zero. So did we check and make sure that x plus 8 is non-zero? We didn't check that. Also, notice that from here to here, did the direction of the inequality, notice that the direction of the inequality is the same. So it's this way, and then it's that way again. So what we're doing, when we move from here to here, multiplying both sides by x plus 8, we are assuming, it assumes that x plus 8 is positive. Because we multiplied both sides. It couldn't be 0 because that's not legal. And it couldn't be negative because apparently we kept the direction. Yeah?
Is it because we're missing the absolute value, or just that's how it works?
There's no absolute value in this exercise.
Okay.
So what happens here is that this assumption is just not correct. So which is false for x less than negative 8. For example, when x is negative 9. So notice that when if x were negative 9, then this factor would be negative 1. We'd be multiplying both sides by negative 1, and we would have needed to flip the direction of the inequality. Now if x is 10, then that'd be 18 and that'd be 18. And so we'd keep it. So whether or not we need to flip the direction of the inequality depends on x. So can you see that this is a little bit slippery? Okay, so now we're going to solve it correctly. And this is called making a sign chart. So solve 3x minus 2 over x plus 8 greater than or equal to 1 using a sign chart. Okay, so now a couple things to say is that as far as like sort of difficulty of exercises this semester, this is probably peak difficulty. It's not really that it's that difficult, in the sense that of every step is like a brain cramp, but rather it's just a process that has to be carried out one step at a time. So it's got to be carried out. All right. But nevertheless, for those of you that are going to end up taking calculus, calculus is a 2-semester course. The first part is usually called differential calculus, and the second part is called integral calculus. And it'd be fair to say that between half and 3/4 of all of differential calculus, the first calculus course, is doing this over and over again. You do this as the main step in something else, where you're doing something, you're making something called a slope chart instead of a sign chart, but it's the exact same thing mechanically. All right, so first step is you need to find the natural domain of this inequality. So that is to say, we need to find everywhere that this inequality is defined. Not everywhere that it's true, just everywhere it has any value at all, false or true. Alternatively, you could think of it like this. Well, what x's can you just not plug into this? Negative 8, because the denominator would be 0. Okay. The natural domain is everything except negative 8, which is to say the inequality is defined everywhere else. All right. The second step, we'll call this 0 and factor. So specifically what we want to do is we want to make one side of the inequality equal to 0, and then we want to factor the non-zero side. All right. So 3x minus 2 over x plus 8 greater than or equal to 1. So the easiest way to make one of the sides 0, I think, is just to subtract 1 from both sides. All right. So is subtracting 1 safe?
Yes.
Yeah, it's always safe. All right. Now we want to combine, we want to get this to be a single fraction. So this part. Make a single fraction. And we'll do so by finding a common denominator. All right. So you could sort of visualize it like this. You could say that this is like 3x minus 2 over x plus 8, and then subtract, say, 1 over 1, greater than or equal to 0. And so we want the denominators to be the same, because when the denominators are the same, we'll be able to add them. So this denominator is 1, so in some sense it's like missing an x plus 8. All right, so then I could say it like this, 3x minus 2 over x plus 8, subtract, and then here's that 1 and here's that 1, and then, I'll put the x plus 8 here, because I wanted this denominator to be like that denominator. But what's the cost of putting an x plus 8 there? Yeah, also putting it up here. Like that. So now it's in both places. And then, this has a 1. And, this implicitly also has a factor of 1 in it. So I can just leave that. So that it looks like this. So 3x minus 2 over x plus 8, and then subtract x plus 8 over x plus 8. So now the denominators are the same. And so now that they're the same, we can just subtract the numerators. So 3x minus 2 subtract x plus 8 over x plus 8 greater than or equal to 0. So I've made an error. What error did I make?
You didn't distribute the subtraction.
Didn't distribute the subtraction, right? Because sort of the general rule that I'm using is that when you're subtracting two fractions and the denominators are the same, so in this case they're both b, then the answer is that this is a minus c, and then all of that over b. So it's that numerator subtract that numerator. So, you know, that numerator subtract that numerator. But the problem is that we need to be subtracting all of x plus 8. But right now, as it's written, we're only subtracting the x, and the 8's being added. So to make this right, if I add these red parentheses, then it's no different than it was before. Those as it turns out, don't affect anything. But these do. Because now it's correct, because now eventually we're going to be subtracting that 8. So can you see it? So generally, it's a good idea whenever you use formulas like this, you can always put parentheses around it. Sort of the problem is that some of the times you don't have to put parentheses, because like the red parentheses actually don't matter, but some of the times they do. They do matter. So that kind of throws people off. All right. Then carrying that out, that would be 2x minus 10 over x plus 8 is greater than or equal to 0. And then I'll factor out the 2 and get 2 multiplied by x minus 5 over x plus 8 greater than or equal to 0. Okay. Any questions about this this algebra? Okay, now I'd like to point something out. So on the previous page, where we were given the same instructions, but I gave an example solution that's just incorrect. In the end, the source of the error was that we multiplied both sides of the inequality by x plus 8, and we didn't try to keep track of if x plus 8 was negative or positive or 0 or what. We just were ignoring that. So that was the problem. So now, we did a lot of algebraic work with an inequality. Now, we started with the same inequality, and then we did something to both sides. We subtracted 1. Now, is that legitimate? Yeah. And then now, look at all of the algebraic steps that we've done. How many of the algebraic steps that we did after that single one occurred to both sides of the inequality? None. We didn't do anything to both sides of the inequality. In fact, what we did is we sort of, the effect of making one of the sides 0 is we're saying we're going to put all the stuff on one side and we're only going to work over here. We're never going to do something to both sides. So because we never did something to both sides, there's no way we could have made an error, because we never did that. It's sort of like you know, your mother's admonition: stop playing on that ladder. You know, because if you don't play on the ladder, you're not going to fall off the ladder, right? Okay, fine. Three. So now we're going to solve an equation, which is curious, because, you know, this exercise is to solve an inequality. So here, in the middle of solving an inequality, we're going to solve an equation. All right, fine. So specifically, we're going to take that inequality. So from step 2, we're going to take that inequality 2 multiplied by x minus 5 over x plus 8 greater than or equal to 0. And we're going to write it down as if it were an equation. So it was an inequality, and then I switched it to an equation. Okay. And now we want to solve this. All right. So specifically, what I'm going to do, it'll be hard. It may be hard to believe, but you know, we want to get x by itself. So I need to get rid of that denominator there. So now I'm going to multiply both sides by x plus 8. And it's at this point that I hope you say, now wait a second. Isn't that what broke it last time? Okay, no dispute that last time we did something with multiplying both sides with x plus 8 and that broke it. Everything went off the rails at that point. But this time it's different. And it's not just, you know, because I promise or anything. There's a reason. Yeah, what's the difference?
Because there's no greater.
Yeah, this is an equation. Right? So we don't need to worry about whether or not we need to reverse the direction of an equation, because that's not even a thing. They don't even have directions. So there's no way, it doesn't matter if x plus 8 happens to be negative or positive. That doesn't matter. So this is an equation, not an inequality. So there's no flipping. But even still, with equations, even still, you're not allowed to multiply both sides by 0. So even that's still not okay. But I claim that we've already demonstrated that we're not multiplying both sides by 0. How do we do that?
We put one side into 0 and then multiply.
Well, that's true. That is what we're doing, but that's not why we're sure that x plus 8 is not 0.
But we already established at the beginning that x is not equal to 8.
Yeah, because the very first thing that we did is we're talking about all the x's that exist except negative 8. That one's out. We're not even mentioning it. It's out. So we know for sure that that's not 0. So we know for sure it's not 0, and it doesn't matter if it's negative or positive. So this is completely legitimate, as opposed to that. So in some sense, what this is illustrating, it's one of the prime differences between equations and inequalities. All right. So and from 1, x equal to 8, negative 8, is not in the natural domain. So x plus 8 cannot be 0. All right. So then the x plus 8's cancel. So then we have 2 times x minus 5 is equal to, well, 0 times that is still 0. So the only answer is just 5. All right. Any question about this? All right, step 4. So this method is named after this step. So this is the name of this step is called sign chart. So what we're going to do is we're going to plot the natural domain from step 1 and the solutions from step 3. So the natural domain from step 1 was everything except -8. So I'm going to make that with a hole there, and I'm going to put a fence here, -8. And then we found a solution in step 3. X equal to 5 is a solution. So I'm going to put this 5 here with a fence post. And so the whole exercise until now has been to get to this place where we took the reals, all the reals, and we cut it into pieces. So what we're saying is, like, there's this piece on the left, this piece in the middle, and this piece over here on the right. There's 3 pieces. And from each piece, we're going to choose a point that's in there. So a point that is to the left of -8, how about -9? That's in there. A point between -8 and 5, how about 4? And a point to the right of 5, how about 6? Okay. Now what we're going to do is we're going to take the sample points, and we're going to, those sample points, 1, 2, 3, and we're going to plug the sample points into the non-zero side of the inequality from step 2. And we're only going to be checking for sign. So so that's the inequality. So what we're going to do is we want to plug into this side. We're only interested in the sign. So specifically, notice that the pattern. Notice the pattern is that that's a 2, that's going to be something, that's going to be something. So in each one of these, I'm going to write down that pattern: 2, and then something over something. 2, something over something. 2, something over something. And at each one of those points, gonna plug it in. So for this one right here, when you plug in -9 into x minus 5, is the result negative or positive? When you plug in -9, it'd be negative. It's -14, but the only thing I need to know is negative. Okay, how about in there? Negative. Negative over negative. So that's two slots. 4 more to go. All right, so at 4, negative over positive. And at 6, positive over positive. Is there any question about those patterns? So this is the pattern. And then down here we'll write the overall sign. Overall. So concerning this, just this one, 2 and then negative over negative, overall that's positive. Right? Summarizing that. How about in the middle region? Negative. And in the rightmost region, positive. Okay, and this thing that we drew here is called a sign chart because it's a chart that's full of signs. And that's how stuff gets named in math. So, fine. So we took the reals, we cut it into pieces, and then for each piece we labeled it as being negative or positive. And it so happened that it was positive, negative, positive. And I could make this be arranged in any way that you like. There happens to be 3 regions. There could have been 4. Or there could have been 44. And they happen to go positive, negative, positive. But any sequence of the words positive and negative, I can make it be that. You could say, well, I make an exercise where it's positive, positive, and then 14 negatives in a row, and then alternating positive and negative 13 times. I could make one that does that. So these could be, in principle, anything. You know, and your task is to figure out exactly what it is. But now that we have this, we can now finally make our conclusion. Now, the way the conclusion works is that we always want either all the negative regions or all the positive regions. And which kind that you want just depends on the exercise. Some exercises will be you want all the negatives, some exercises you want all the positives. It'll just depend. So you have to be able to look at it and figure out which are the ones that we want. So do we want all the negative regions or all the positive regions, and why do we want that kind? And in the end, it has to do with we're trying to find the points where this inequality is true. Sorry?
So it ties back into the inequality, and then it's something like this, which is greater than 0.
Uh-huh.
Then they want all the ones.
Exactly that. Notice that it says this thing greater than or equal to 0. So we want the positive regions. The reason why is exactly that. Now, if we were to go back in time and edit the exercise to make an alternate history, if I had said solve this, how could I edit it to make it to where in the end we wouldn't want the positive regions, rather we would want the negative ones?
If it's not equal 8. Yes. Flip the.
Yeah, flip that. If that inequality was going the other way, then you just do a copy, do a search and replace, all the way through the thing, and all of these would be going the other way, other way, and then this would be pointing the other way, and this would say blah blah less or equal to 0, and we'd want the negative ones. All right. So there's 2 positive regions, that one and that one. And so that's an interval and an interval. So the answer is going to be the union of 2 intervals. So let's write that down. So the interval on the left is negative infinity to negative 8. And now we have to figure out, do we want negative 8? Is it part of the solution, or is it not part of the solution? It is not? So you're saying I should make this open like that. Now, why is it not part of the solution? Because
Oh, well,
Yeah,
no,
negative.
you end up dividing by 0 if negative things in there.
right,
Yeah, which is impossible.
right. So negative 8 can't be included because it's not in the natural domain. because the question is we want to know, when is this inequality true? Well, at -8, it's definitely not true because it's not even defined there. Okay. Similarly, an interval 5 and onward, so 5 to infinity, so union 5 to infinity. So we never include infinity because it's not a number. But what about 5? Do we include 5? Why?
Blank circle.
That, well, I don't dispute that. It's filled in, but that's not the reason.
It's in the natural domain.
I do agree that it's in the natural domain. That is true, but that's also not the reason.
That's when we plug it in, it's greater than or equal to 0.
Because when you plug it into the inequality, the result is true. That's why. Because the inequality is true. At x equal 5. Specifically, it would look like this. It would be 2 multiplied by 0 over 13 greater than or equal to 0, and so the inequality reads 0 greater than or equal to 0, which is true. Right? And we're looking for all the points where the inequality is true. So now, again, to consider an alternate history, we said that as it happens in this exercise, we want the positive regions. Now, we could go back in time and edit the statement of the exercise and flip the inequality around so that here we would say we want the negative regions. We want the other ones. Now, how could we go back in time and say, okay, we still want the positive regions, but in fact, 5 is not part of the solution? How can we change it?
Just make it, take away the greater than or equal to, just make it greater than.
Just make it greater than. Because right now it says greater or equal. And if we were to make it just greater, and replace all these with just greater, then this would still be just greater. We'd still want the positive regions, but then we'd get to right here, and the inequality would read 0 greater than 0, which is false. So the reason why I'm pointing this out is because it can be subtle, right? The reason why I made this one open is that's a signal to me and to the the grader that that's not even in the natural domain. The reason why I made this one filled is because I'm saying that that's a point that is in the natural domain. So that means that that the inequality is defined there. It might be false, it might be true. And then finally, yes, we do definitely want that point because, as it turns out, the inequality is true there. So now, in summary, we're way over. Wow. In summary, this is it's complicated, but this is what's required to get credit on this exercise. And essentially all this stuff in red, this is just me giving commentary. You don't need to write that stuff. One or two. So when you get this can easily be done on a single page. Yeah, you don't need to write all this junk. All right, so I hope you all have a wonderful Monday.